today as well. This is the second part of our webinars that we are holding. And the first part of our webinar, let's actually go into full presentation mode. On the first part of our webinar, we covered the philosophy of deep excavation design. We identified the issues that we have, that an engineer needs to look at. We understood soil response. We looked a little bit on geotechnical investigations. We looked at the various wall systems, support systems, tiebacks, anchors, struts, rakers, and so on, and at the analysis methods we have available. In this part of the presentation and webinar, we will be looking at the design approach and codes. We'll be working with design examples, and we'll be looking at some case histories and what the impact is of using the different design approach or methods in each one of them. So we're going to do a little overview of part one, just to make sure that everybody's on board, because some people might not have attended or seen part one, but we'll just make a short summary here. We distinguish between cohesive and frictional materials, basically clays and undrained response, and sands on the other hand, as an approximation, of course. We saw that apparent earth pressure diagrams are not soil properties, they are dependent on the soil structure interaction. Also saw that we had different analysis methods, the conventional, limit equilibrium, and so on, elastoplastic with Winkler springs and finite element methods. And the whole idea between all these analysis methods is to obtain wall moments, displacements, support forces, shear forces, so we can design all the structural elements of an excavation. That is the wall and the supports. On the conventional methods, we've seen that for multiple supports, and in general, we're assuming some sort of lateral earth pressure distribution behind the wall. We're determining the fixed locations for the forces, and especially below the excavation. We're analyzing then the wall beam with assumed loads. The advantage, of course, of conventional methods are that it's an easy method to vary. It gives a backcheck for more rigorous methods like elastoplastic or finite element. The disadvantage is that the conventional method ignores soil structure interaction. So let's look, if we look into conventional methods, the idea is that we're assuming apparent earth pressures or some sort of lateral earth pressure distribution. We're also calculating our external surcharges. We have our net water pressures, our seismic pressures if we have an earthquake event. You might have other effects as well. The idea is that you add all of them, you adjust them for your pile spacing effects if you have especially a soldier pile system, and then you come back with a line load behind your wall. You use that line load and you basically are loading a beam and you're doing some form of a structural analysis. When it's coming down to calculating our wall embedment safety factors, we had three safety factors that we're looking at. One is based on the horizontal force, so we're just looking at the forces below the lowest support. There's driving forces, resisting forces, and expressing that ratio will give us a safety factor based on horizontal force. We can always look at the rotational or moment safety factor, where we're taking the moment below the lowest support, resisting and driving. And there's also a length-based safety factor, which by finding a safety factor of 1 for either the force or the moment, whichever is more critical, then we can express the safety factor as the available length divided by what is required for a safety factor of 1. We looked at the beam or elastoplastic foundations. There's two ways of doing this type of analysis. One is that you're assuming driving earth pressure behind the wall, and you're using passive soil springs. The other is that you use active and passive soil springs. We've seen that with just the driving pressures assumed behind the wall, there's no state dependency, whereas you can capture some sort of state dependency if you're using active and passive soil springs. We've also seen that with finite element analysis, the idea is that we divide the smaller elements. We still have to include all the construction staging. That's the important of soil structure interaction that you have to build up on your previous states. We divide the soil, we create structural elements, we create boundary conditions, and we're capturing state by state what's happening. We're going to do a small review of the different methods. So we had Blum's method for multiple supports and conventional analysis. So we have a continuous beam, the net loading diagram here, and we're establishing a virtual support point where the net loading diagram is going to 0. So we're getting a continuous beam here, and we're calculating the support reactions. We're getting a reaction at the base, expressing that safety factor on the passive force that way. The FHWA simple span approach, if you remember from the last webinar, it produced the smallest moments from all the available methods, but it is prescribed in an FHWA manual, so that's another question. But we'll see that we'll see further down what's happening as well. So we're assuming a virtual support at the excavation subgrade, and the available resistance is whatever it is here. This is driving. So again, we're expressing a horizontal safety factor. Then there's modified FHWA Blum method. One of the things with the FHWA approach is that we're not assuming that the wall is really continuous. The method, what it's doing is that it's taking from the top of the wall to the bottom support, it's like a single beam, whereas we're doing a simple span below and another simple span below the lowest support, all the way to wherever that virtual support is assumed. So here, if we do modification of the two, we're going back to the net 0 point, or our net loading, and we're assuming that virtual support point there. Again, we get the reaction, and we're expressing our passive safety factor. And there's also the Caltrans method, again, very similar to the FHWA approach in that the wall beam is not continuous. There's a beam that's being modeled from top to the second support, simple span thereafter, and the lowest support. We're finding that virtual support point simply by going out and establishing a moment equilibrium. So we're taking moments below the lowest support, ignoring all the thrusts above here. One of the things is that once you do that, we're going to be getting no reaction at that point of virtual support, no horizontal reaction, because everything balances out. Now, there is different ways over the years of designing deep excavations. The traditional way is the allowable design, where we're assuming some safety factor on the capacity of the systems, and we conservatively assume soil properties. We'll look into that. Another way in the US is the load and resistance factor design, LRFD. It's really mandated mostly by DOTs, Departments of Transportation, highway projects, railways. So they ask for it because they have to be compliant with LRFD, all their projects. But we'll see that there are some challenges. And in Europe and some other parts of the world, there's some ultimate limit state design, what's called the ULS, we're calling here, Eurocode 7. The idea is that you imply some partial factors into strengths, loads, and so on. And you create a series of combinations. Now let's look at the allowable stress design or allowable design methodology. So the idea, this is what has been done for ages. We conservatively assume soil properties. We determine the lateral pressures on the wall, whatever that is, soil, water, surcharges, and so on. We're using an analysis method to determine the support reactions. We're determining the wall embedment with an appropriate safety factor. We're determining the bending moments on the walls and the shear forces as well. And then we design the structural and geotechnical elements with the safety factor and their ultimate capacity, really. And in some cases, like the allowable stress steel design, the safety factor is already incorporated in the allowable stress code. Now we're going to be working first of all through an example. Again, we're going to be looking at this 50-foot excavation, 15 meters. I know it's not the deepest. I got some comments when we sent out the latest newsletter. Oh, you know, in this place of the world, we're doing an excavation 35 meters, which is like 100 feet. So, you know, sure, we've done excavations like that as well, all right? But, you know, we want to make something more reasonable for most people that are working. Not everybody goes 100 feet every day for an excavation. Of course, there are some privileged people that do it, but that's another story. So let's assume our soil profile here, 0 to 50 feet. We have this F layer, which is the sand, gamma 120 pounds per cubic foot. That's roughly 19 kilonewtons per cubic meter, and friction angle of 30 degrees. Below 50 feet, below 50 meters, 125, closer to 20 kilonewtons per cubic meter. 36 degrees friction angle and effective cohesion of 100. We're going to assume the groundwater at minus 35 feet, that's roughly minus 11 meters. That's the density in pounds per cubic foot. I'm sure some of you in the metric wall will be surprised at these units, but we are based in the US, so we have to include them. So we're going to be assuming the same hydraulic permeability for both soils. The ground is going to be horizontal, and we're going to have tieback supports at 8, 22, and 36 feet depths. 8 feet is basically around 2.5 meters. 22, we're looking at 7.5 or so. And 36, we're looking at 12 meters depth. We're going to have the tiebacks at 20 degrees from the horizontal. This is what our excavation looks like. We're going to do this allowable design sample, and we're going to assume FHWA apparent earth pressures, and we're going to be assuming full passive pressures on the resisting side. It's an assumption. You can make different assumptions here if you want, without wall friction. So, calculating the Rankine active earth, lateral earth pressure coefficient, with 30 degrees it comes to 0.33, and the passive coefficient for horizontal ground comes to 3.0. For soils S1, respectively, it comes to 0.26 and 3.852. Before we establish lateral earth pressures, one of the first things that we have to do is we have to establish our water pressures. So we're going to do a one-dimensional flow, and because we have the same permeability, we did this so the calculations are simpler. For this example, we have the hydraulic head loss, 15 feet. We have the total travel path. We're calculating a hydraulic gradient, 15 feet divided by the travel path, and then we can express the total hydraulic head as the initial minus the losses. So we're calculating the losses times the travel path, and we're coming down to calculating the total, the pressure head, and based on that we can calculate the water pressures. So once we have the water pressures, we'll see that right at the excavation level, we have the maximum net water pressure, and then below, it drops to 0 at the bottom of the wall. Now, if somebody was to assume hydrostatic water pressures, there will be a slightly different value here, but the diagram will be dropping, will be constant. There will be a question, though, if you have soil under you, you will be getting flow. So when you're assuming, if you assume hydrostatic water pressure, you're doing two things. One of them is that you're, of course, increasing the driving forces due to the water, but you're also reducing the driving soil forces because you have increased water pressures. And the other thing that you're doing is that on the excavation side, you're of course decreasing the water pressures, but you're increasing the passive soil pressure. So, I'm in favor of generally keeping realistic water pressures or a model that is realistic. But there might be some other cases where you get separation where hydrostatic water pressure envelope might be more appropriate. So now that we have our water pressures, our next task is really to establish our active and passive pressures. Even though they might not be fully experienced, we're going to be needing them. So we're establishing two tables: elevations, unit weights of soil, the total vertical stress, our water pressures, our effective vertical stress, our effective cohesion, our active lateral earth pressure coefficients, and then we calculate with this equation the active pressure, making sure that this value doesn't increase, doesn't drop below 0. So we have the active earth pressure as Ka times sigma prime V minus 2 times the effective cohesion, square root of Ka. And then we created the table for the passive pressures here, looking at from elevation minus 50 to minus 75, unit weights. Again, the same concept with calculating the vertical effective stress, effective cohesion, Kp, and our passive pressure is being calculated here. Of course, we don't have anything above 50 feet because we have excavated the soil. So once we're there, this is what our active earth pressure diagram looks like. Now, some engineers use active earth pressure diagrams for multiple supports. If you have very conservative soil properties, you can be fine, but you have to look into all stages, and it's theoretically inconsistent if you're doing that. So that's what the active earth pressures look like. So the idea is that with FHWA approach, we have to integrate the active thrust. We're using a factor of 1.3. So we integrate all the different components above and below the water table, and we'll come back with 62.66 kips per linear foot with a factor of 1.3. Now, in some codes, in some other specifications that I've seen around, not FHWA necessarily, you might be actually playing with this 1.3. There's a recommendation to lower it as much as 1.1 for some type of structures. So next we have to establish our apparent earth pressure diagram. And what FHWA recommends, which I think is reasonable, is that you need to locate this top and bottom portions of your diagram based on where your top and bottom supports are located. So this H1 and H2 are basically 2/3 of the height, H2 from the bottom of the excavation to your lowest support, and for H1 from the top of the wall to the support, so H1 is 2/3 of that height. So once we have that, there is somebody. If you have questions, all right, please use the chat and write your question on the chat. Christian Radu has a, Christian, if you have a question, please use the chat. That's the only way I can see that you write something, because I cannot see that otherwise. So the idea is that we're calculating the apparent earth pressures here. We're coming back with the apparent earth pressure diagram. Now, one of the things with these diagrams is that really, in some cases, they don't distinguish between what's happening above your water table and below your water table. We're actually putting forward some recommendations on how this can be handled. There's also some other recommendations around. So we're establishing again the net loading. We have our lateral earth pressures, our net water pressures, and our net loading diagram. And we're going to be using the Caltrans method, so we're going to be doing a moment equilibrium. So we're separating here manually. If we were to do this by hand, we'll separate each thrust component. Minus 36 elevation is our lowest support. Excavation at minus 50. And then we're trying here on the resisting forces to find this length where we can balance out the moments with all these thrusts. I usually like to do it, if I do it manually, I'll do it trial and error. So I'll progressively change that elevation. We're forming basically a table with our driving forces, the total force, the moment arm to the centroid of its component, and the moment, and this is the total driving force, 227.3 in this case, and then we have a resisting force below that net point, zero net point, and we're calculating here by progressively changing that elevation. that we're coming back with elevation minus 67.007 in this case, where we're matching out exactly what the driving moment is. So the idea then with FHWA, we subdivide the wall beam. In this case, we have 3 supports, so we have a continuous beam from the top to the second support here. Then we have a simple span moment on the next level between the second support and the third. And below the third, we have another simple span. And now, once we have applied the loads, we'll see what the moment diagrams are, what the reactions are. So we're adding, the first reaction is fine, we can take the load directly from here, horizontally at least. On the second reaction, we have to add the 2 components, this and this. And on the third level, we have to add this and this horizontal component. And we also get our bending moment diagrams. Okay, if you're not, let's actually hear, somebody not hearing the audio. If you're not hearing the audio, use the option call using computer. So, one of the things that we'll see is that the reaction here at the very bottom is actually very close to 0. That's actually the verification that we've done our modeling correctly, in this case for Caltrans. So it's not never going to be exactly 0 because of rounding and other things, but if it is very close to 0, you're fine. So once we have our analysis, we can look into our model. We have to take our support reactions and resolve them in the direction of the tiebacks at 20 degrees. And we have our simple span moment diagrams that look like that overall. When we have to calculate the wall embedment safety factor, again, we're calculating, we have all the active, or the pressure structure on the active side, or so let's say the retained side, and on the resisting side, and we're taking moments again. And in this case, with a 25-foot wall embedment, we found out that the rotational safety factor is 1.456. If you follow Caltrans, they're just requiring 1.3, and the wall embedment comes to 23 feet. Now, I won't say, this is your final design, but, it's just for this example that, this is what the numbers are. Now, when we go into design the allowable wall bending design, we have our maximum moment, we have our stress, yield stress of the steel, 50 KSI, that's 355 megapascal. So if you follow that, an allowable stress design will be an allowable stress factor, 0.6 in this case, times 50 KSI, that's your allowable stress. If we ignore the axial load on the wall, so we keep it a little bit simpler, the required elastic section modulus is 39.32 inches cubed per feet. So, this is a number that we're actually going to be using later on to compare the different design approaches and like LRFD and Eurocode, and see what required section modulus they come back with. We're going to design our ground anchors or tiebacks. So we're assuming a presumptive ultimate bond resistance on the fixed part between the tieback and the soil. Traditionally, we've been using a safety factor of 2 on presumptive values. We're assuming the fixed bond diameter, let's say 6 inches. We're determining the fixed length of the tieback, excuse me, and the allowable tilting capacity then calculated as our length times our bond resistance times the diameter times a pi times divided by the safety factor of 2, or whatever else you want to use. On the structural capacity with high strength steel, traditionally for temporary excavations it has been 0.6 times your area of steel times your Fy, where Fy is 270 KSI or 1862 megapascal, at least for strand anchors. Now let's look into LRFD. load resistance and factor design. As we said, it was adopted in the United States, especially by ASTO. And the reason they have adopted it is because they have all these bridges where there's all different structural sorts of combinations. So the idea is that you combine loads, you multiply loads by a factor, you divide the resistances by a resistance factor, and it tends to be quite cumbersome. Even DOTs themselves find it very difficult to use. Engineers also find it very complicated. We'll see that you can have quite some inconsistencies, and these inconsistencies are probably due to lack of guidance and proper calibration. And I'm not the only one that's actually saying not to use ASTO LRFD combinations for excavations. There's also some other not-professionals, I don't want to quote their name right now. They're actually teaching a course on LRFD, and they say do not use it for design. And it's funny. It's, you know, LRFD is a design. It's a design build code, right? And if your leading experts are saying do not use for design for deep excavations, you should be thinking that ASTO should be doing something to address this issue, and all the authorities, but they haven't done so yet. So anyway, let's look and let's see what's happening. So the idea, if you have multiple supports in cases we have apparent earth pressures, the idea is we're using a safety factor of 1.35 on the earth loads. And if you have cantilever cases or active earth pressures, you're going to use 1.5 safety factor. And on the resistance side, if you have passive pressures or any resisting force, you'll apply a factor of 0.75 to reduce that resistance. Now that has been calibrated into limit equilibrium analysis, and I don't know what kind of calibrations they've done, but there's no guidance on what to do when you have a nonlinear analysis. And as we've seen with deep excavations, it's always important to do soil structure interaction. So, you know, if you have something which has many levels of supports, your limit equilibrium method might not be appropriate. So you need to have an appropriate design approach, even with LRFD, to design your excavation. Apparently, they haven't done that. So let's look into some of the combinations. There's strength 1 combinations, strength 2, strength 3, and so on, and going down to extreme events. In essence, for excavations, we're just having the factors on the live loads being different. So there's between strength 1 and strength 2, the 175 and 135. And at rest earth pressures also get the safety factor of 1.35 as well, if you have to note this as well here. So looking at the same example, strength 1A load combination. Remember the bending moment was 98.3. Following that approach here and just multiplying the earth pressures and dividing the resistances, we come back with an ultimate moment right now, of course, of 206 Gibbs feet. So let's actually see what that means. The required wall length goes from 23 feet to 28. So we have a 22% increase over allowable stress design. Our wall moment goes to 206. Now, if we say because it's an ultimate design, we have a fee of 0.29, our allowable is 45 KSI, much closer to the 355 megapascal, almost let's say like 300 megapascal allowable, our actual, let's say, design strength. We're ignoring the axial load to keep this thing simple. So after we do all these nice calculations, we're coming back that we need a 40% increase in the required elastic section modulus of the steel for this excavation. So same design, if you did it in allowable stress design, you'll be saving money. Looking at the ground anchor, if we did the same thing, there's just a 13% increase versus allowable stress on the required steel. So here in the support reactions, the difference is smaller. Now let's actually start the same example and look at it with ultimate limit state approaches like Eurocode. What I have to say about Eurocode is that they have put more thought into it, but unfortunately it's not as mature of a code as it as the American counterpart of the code is. And now I can say that because the Eurocode doesn't have a real dedicated commentary, you can see how it's formulated. Hopefully, the next edition of Eurocode that will come will be much better and will include commentaries, and we'll see, what's to happen with that. But the general idea is that you're defining different states where failure could potentially happen, and you're trying to, of course, avoid it. So we have EQU, loss of equilibrium of the structure or the ground, considered as a rigid body in which the strengths of the structural materials and the ground are insignificant in providing resistance. STR, internal failure at the structural or excessive deformation of the structure or structural elements in which the strength of the structural material is significant, providing resistance. Geo for geotechnical, failure or excessive deformation of the ground in which the strength of the soil or rock is significant, providing resistance. And then you have uplift and hydraulic heave for hydraulic events, for hydraulic flow and so on, piping and so on. So the idea is that they define what we would call otherwise combinations in load combination in the United States, but you don't necessarily have to add all the factors directly. So the idea is that you have this A1, M1, A1 on actions, A factors on actions, M on material strengths, and R on resistances. So there's design approach one where you have to run two combinations, A1 and A2 and 2R1. Basically, when you see an M1 here, the material strengths are not affected. We'll see what is R. Then there's design approach 2, where there is A1, M1, R2. In R2, there is a factor on the resistances. There's design approach 3, which in excavations really resolves back to design approach 2, unless these R3 factors are different. So, just to illustrate, it's a more comprehensive approach. There's different methods. One of the things that I want to say here, for me not to skip this, it's not necessarily that you're going to be adding this directly. The Eurocode allows you to amplify the effect. So you could actually, in theory, run an equivalent analysis, and we'll see how that can happen. So again, it's impractical to perform calculations by hand. It's a lot of individual partial safety factors, and if you were to do this by hand, you're going to be losing a lot of time finding out the appropriate factor. And just to point out, it had taken me, I was reviewing Eurocodes for 2 years before I even started programming and adding something. So it's quite cumbersome. They could do a better job describing it more easily, I would think. So anyway, let's look into the various set of factors. On our A1 factors, they're dividing for actions or external load, let's say, factors for permanent and variable based on the type of load or action. Unfavorable, the ones that are pushing against our excavation. Permanent will be our S pressure, we'll get a factor of 1.35. Variable, like external surcharges, will get 1.5. In the A2 combination, the permanent loads, the variable loads will get a factor of 1.3. Then on the partial factors on soil strengths or soil parameters, with the M1 set, everything is unity. With the M2, the angle of shearing resistance or the friction angle is basically adjusted according to the tangent of the friction angle with a factor of 1.25. Our effective cohesion is divided by 1.25. Undrained shear strength by 1.4 and confined. And weight density, it's the same, which I think is wise. We'll see here this 1.4, in some cases, will really lead to very funny results. So we're going to look further down the road at the very deep excavation of 2 meters that requires 12 meters of wall embedment. So just to put into perspective, for our American friends here in the United States and everybody, so we're going to be looking at the 6-foot excavation that requires 36 feet of embedment, roughly. 36 feet of embedment, roughly. 36 feet of embedment. 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 So let's look into design approach 1, combination 1, 1.35 factor on apparent pressures. We're calculating our moments and section modulus, so that's 20% more steel compared to the allowable stress design, and just 10% more steel on the ground anchors. Looking at design combination 2, where we're reducing the soil strength. Remember 1.25 on the tangent of the friction angle, and 1.25 on the effective cohesion, 1.4 on the drain shear strength. We need a 27% more, we should say section modulus. Here 125.7, 185.7 that keeps feet per foot. And the anchor is just 3% more steel. And they require wall embedment. We're requiring 17% increase, so we're going to 27 feet. Looking into design approach 2, 1.35 on apparent test pressures, 1.4 on the passive. Our bending moment goes to 260. We need 76% greater section modulus, we shouldn't say more steel here. The anchor force, we need 25.4% more steel, and the required wall embedment, we need 82% more for our wall embedment. So let's compare the requirements. Allowable stress design here, moment, section modulus. This is, we're not requiring any increase in steel. Looking into all the combinations, the ultimate moments range from 180 to 165% of the allowable stress design, whereas the reactions range from 137 to 167% of the allowable stress design. So the reactions will be much closer matched to what our allowable stress design experience is, but for the ultimate moments, I would say that we're generally off. So a question becomes, okay, Dimitris, we've done the limit equilibrium analysis. How do you do a nonlinear analysis using LRFD or Eurocode 7? So they have been calibrated on conventional methods, but we know that the performance of excavation depends on construction staging. So the question is, let's say that you're using one of these M2 combinations, you're modeling your nonlinear analysis, and on the first stage you get 15 centimeters of movement, let's say close to 4.5 inches. And you continue building your excavation at least your modeler, right? Not in reality. If you're on your first stage where you excavated 8 feet or 10 feet, you got that much movement, your employers will be already behind you, and you won't be able to go anywhere further, at least in the United States. I don't know in other parts of the world. So, you're building up on all these unrealistic displacements, a model which, then you say, this is my ultimate limit state. And the reality is that that case will probably never materialize. But anyway, let's actually see how you can actually theoretically do it. And then once you have the theory, you can judge for yourself if it is appropriate or not. So one approach is to adjust the KAs, KPs, effective cohesion, and drain shear strength to produce the equivalent effect. You multiply the surcharge by the load factors. Now, ASTO doesn't specifically mention what to do, but one idea, and following Eurocode 7, is to standardize your initial analysis by the unfavorable lateral earth pressure factor, 1.35, when you have multiple supports, which is also the factor in Eurocode 7, design approach 1, combination 1. And then at the very end, multiply the results times that factor. So Eurocode 7 allows you to multiply the effects at the very end. Design approach 1, combination 1 will actually lead to reasonable results, more or less. We've seen that the design approach that uses the factor M2, where you're reducing soil strength, may produce unrealistic response. But this combination can still show you where your structure is sensitive or where your excavation is sensitive when you have a geotechnical issue with the strength. And we're also going to show you that M2 combinations might not work well when you have clays, especially softer clays. So the idea, I guess, with this effective on actions, just to illustrate it, let's say that this is our initial excavation. These are our real cases, real case here. So we have a 10 kPa load. So in order, if we have a 1.35 factor on the earth and 1.5 on the permanent, let's say on the load. So what we're going to do is that we're going to take this load times 1.5 divided by 1.35, and we're going to come back with 11.11 kPa for this surcharge. And we're going to run the analysis without factoring our active or passive earth pressure coefficients. And at the very end, whatever moment we get here, we're going to multiply times 1.35 to get our design value. So we did this with the same example with a nonlinear analysis. We got displacement from 1.6 inches to 6.1 inches with ASTO and 5.0 with combination 2 from Eurocode. Again, we saw that the ultimate moments range from 135% to 218.2% of the service case. Design approach combination 1 was the one that produced the more reasonable structural results here. And the reactions, again, displayed a much smaller variation compared to the moments on the wall. Now we also look at clays. So we have a clay, we've replaced the lower layer with a clay which has an undrained shear strength of 220/50 PSF. That's like a medium stiff clay. Again, around the same comparison, very large displacements in some of the combinations, like 8 inches. And of course, the bending moments going from 135 to 212, again, of our service case. And our reactions, actually, our reaction now starting not behaving that well. And that's actually because in some cases, your pre-stress effects play a role. So, you know, the level of pre-stress that you assume on your walls can make a difference. So the reactors actually showed the smaller variation, so they went from 122% to 135% of the support pre-stress. And now we're going to look at the infamous 2-meter excavation, 6.5 feet, 2-meter of fill, 30 degrees, 19 kilonewton per cubic meter. So, you know, we have to have a balance between the metric and the imperial world. So that's like 120 pounds per cubic foot roughly. And below that, we're going to have a soft clay with an undrained shear strength of 15 kPa or 313 pounds per square foot. We're going to do the free earth method, and based on where we find the wall moment to be 0, we're going to require a safety factor of 1.5 based on that. So by doing that, we're coming back that we need a wall embedment of 3.2 meters. And, you know, you'll go out, you'll build this, you might get some wall displacement, some basal movements because of soft clay, but it works. Everybody knows it works. But now let's see what happens when you start applying Eurocode to it and ASTO. So this is our net loading diagram for the service case. We need 3.2 meters. If we go to design approach 1, where we're multiplying the active pressures by times 1.5, not 1.35, we see that the net loading diagram progressively with depth starts decreasing, which tells us that this is becoming inherently unstable with depth. If we look at design approach 2, where we're reducing our soil strengths and especially our effective cohesion, so our undrained shear strength, I should say, is divided by 1.4. So from 15 kPa, we went to roughly 11. There's very small net pressure here on the passive side. And we need, for this 2-meter excavation, more than 12.5 meters of wall embedment to satisfy equilibrium. Of course, you seem like looking like on sideways because this is an issue. It's not going to happen. So it's one of those things that you've calibrated nicely your models for and your load factors for some specific case, but then you forget to check about your reality. So, looking at design approach 2 for Eurocode 7, unstable. You cannot make that work unless you do some $1 billion or €1 billion soil improvement. Not that ASTO is any different. So you follow ASTO load combinations. Let's say you have to do something right next to a bridge. They're going to tell you, oh, this is unstable. You have to spend $1 million as well to do soil improvement for this excavation. So with this, we're going to be looking at 6 excavations, real projects. So we have excavations that are ranging from 15 meters roughly to 23. What we've done is that we've looked at their wall displacements from in kilometers, and we try to match the wall displacements with the nonlinear analysis method, get the bending moment support reactions, match the support reactions when we had them. These were basically projects in the United States. There were stiff clay, some of them in Boston, some of them in Washington, D.C., and in San Francisco, one of them. So we ran the analysis for various cases for the service case, of course, and then for ASTO LRFD. We looked at the displacements, we matched the soil properties, and then we also ran a limit equilibrium analysis with FHWA. We did this and we checked the ratios of forces. We also looked at the, if you remember, the FHWA approach assumed the pinned reaction at the supports at the excavation subgrade. So what we saw was that there was, in some cases, your safety factors, actually when you apply the Eurocodes or something else, they tend to be smaller. So there were some cases where you got a smaller safety factor on wall bending moment using a design approach or LRFD than you will otherwise get. And some of that had to do with how you were, in some cases, restraining, or how your lateral earth pressures had to do, or how your water pressures were modeled. Because if your water pressure was controlling really everything, there is no factor on your water pressures in some cases. Then we saw that the overall factor on safety support reactions ranged in some cases from 1.0 to 1.4. There were cases where doing an LRFD approach and a nonlinear analysis produced no safety factor whatsoever. On the limit equilibrium analysis with FHWA, we saw that the bending moments were from 19 to 66% of the nonlinear analysis. This is consistent with our previous results. So we don't think that that approach with a simple span bending moment to the excavation subgrade should be used. And the support reactions range from 53% to 178% in the limit equilibrium analysis. So, the reactions were really much different in some cases. And that's, what happens is, sometimes you actually change the whole response of the excavation, so what you get really doesn't make sense. So in our general experience, for limit equilibrium conventional methods, you have to make sure that you select an appropriate method. It's really good for back checks. We're encouraging that nonlinear analysis methods are performed. We have to warn you that the ultimate limit state and LRFD procedures may produce inconsistent results based on our allowable design experience. And when I mean our allowable design experience, I don't mean only our own allowable experience, but also what people have been doing for the last 60 years. You always have to pay attention to details and always inspect results. And next week, we're going to be holding seminars on optimization of excavations. So we're going to be showcasing our software and how you can do different things and what we've seen in the last 2 webinars. We have to also make a living. So this concludes this part of the webinar. We're going to be sending a detailed example. I want to thank everybody for attending. If you didn't hear us, we'll be sending the video at the very end and PDF. So I'll be happy to answer any questions right now. There's a question from Walid. Thank you for, I have a question about clay underwater. Do you treat it like the sand? Do you add the water pressure triangle? Okay, so that's a good question actually. It depends really. The water pressure should be really added separately. The diagrams by Peck, 0.2, 0.3. When I talked with Peck, when he was Dr. Peck, he was still alive, he said that these are based on effective pressures. So if you are above or below the excavation, your water should be added separately. And my approach is always to take water pressure separately. Any other questions, please? Vivek, Christian, do you have any questions? I saw you raise your hand. Okay, so Vivek had a question. What about excavation in rocks? How different will it be? Actually, in rocks, excavations can be, mechanics can still are similar, but in rocks it really depends on how your layering and fracturing of the rock is. You can still analyze it using an effective cohesion and a friction angle. There are recommendations to do that. But in reality is that how your joints are oriented compared to your excavation will make a very huge difference. Any other questions, please? You can always email me if you have any other requests or any other questions specifically. And if you haven't connected with me on LinkedIn, please do so. When you did the CPATS flow, I guess it's hard to use the buoyant unit weight. I'm always against using the buoyant unit weight. The reason I'm against using the buoyant unit weight because it is only applicable when you have hydrostatic water pressures. That's the only case where your buoyant unit weight is applicable. Otherwise, you have to always remember that your effective stresses are total minus water pressures, always. So that's why I prefer to do always that, and I never use buoyant weight. But I'll use boy and coffee for the time being a little bit. It's still morning here. Any other questions, please? So, with Eurocodes and LRFD, it seems that, okay, there's a question from Vivek. How important is time as a factor in deep excavations? And time is important when you have really clays, I would say, or time-sensitive soils. So if you have clays that behave in an undrained way, then switching from undrained response to drained over long term can have an impact. What kind of nonlinearity you keep mentioning? Okay, first of all, nonlinearity is our soil response. It's never linear. It's always have some elastoplastic response where when you press the soil, it won't go as a linear curve with strain and stress, but it has a curved approach. So that's the general idea. So all those, so what happens is if you follow just a traditional structural design to deep excavations, you're ignoring all those nonlinear soil interactions with the structure be that the wall, the tiebacks, and so on. Okay, there's a question that the excavation going down also fluctuates the water table. How will this affect the design of temporary retaining structure design? Well, you have to analyze it. So it changes your water pressures. Whatever changes your water pressures changes your effective vertical stresses, and as a result also changes your horizontal stresses. So you have to analyze it. That's why you do a flow net analysis. But theoretically, right, if your fluctuations are very small, you really have a cyclic loading, but that's not really taken into account. Like you're assuming small fluctuation when you're at a given state. How do you account for? There's a question. How do you account for that in a nonlinear analysis? Actually, we gave some details on the first webinar, and that's based on how you model the soil elasticity. So if you watch the first webinar, you can use different soil models, and depending on how you model your soil springs or your finite element analysis, you can have soil springs that are nonlinear, and you can also have finite elements, discrete triangle or rectangular or whatever else you use that have nonlinear response. Any other questions, please? Not really. There's a question, so it has to be finite elements. Not really finite elements. Finite elements is one option. Elastoplastic Winkler springs is another. And in some cases, finite elements might not necessarily produce realistic results. If you have, you tend to overestimate the basal movements and how much uplift you get on excavation. So, you can get, it depends really how you want to analyze, but not only finite elements. We always recommend that you use at least 2 methods of looking at an excavation, and we'll always do that. So if we're using FEM, then what should be the alert level or work suspension level based on the results obtained from the analysis? Well, I will have to specifically look into your excavation. But you have to set, first of all, some displacement levels. So there's a question from one of the engineers here. Second pile wall with pristine circle pale ULS results, no anchors. Moments and shear forces were always higher with an anchor. So if I understand correctly, Alexander, you're saying that when you have an anchor, you always go to higher shear forces with ULS, but not with the cantilever case. My problem with the ULS methods is really that they tend to produce quite a scatter on the results. So, you do an example, right? It works fine, especially if you look at sands. The results will tend to be more reasonable, but not always. So my issue is that, depending on what approach you follow, and, from all the combinations I've seen, there is design approach 1, which I think is probably the closest thing you get to an allowable stress design. But then, you combine it with combination 2, so it really depends. You're going to get the purpose of this presentation was really to show you that you get quite a big scatter. So I guess, what we've shown here is that you generally get higher moments especially. I mean, that's what we have seen. And but support forces, will tend to be comparable. It also depends where are you located, Alexander? Okay, Ireland. So you're following design approach 1 with combinations 1 and combinations 2. So the structural approach is fine, DA1, but when you use the combination 2, it really depends on what your effective cohesions are and clay strengths. There's a question regarding their stiffness. That's a good question, and it has come up before. I always recommend using a hyperbolic or nonlinear model of elasticity with a linear load reload. I think that's the more realistic, one of the most realistic soil moduli that we have. So you get, there's ways of estimating that. If you have a CPT or a triaxial test, that's how you obtain it. And of course, you have to keep in mind that Eurocodes don't really do anything with the modulus of elasticity. Theoretically, you could study the effect and what happens when you change it. Now, perhaps in the near future, you'll have an automatic statistical analysis. You input in your elasticity with some ranges. And you have to keep in mind that sometimes just prescribing a softer elastic model doesn't necessarily mean that you're going to get bigger moments. Oops, I have a lot of emails. Is SPT, okay, the modulus of elasticity for each load step in laboratory tests is different. So from your point of view, is SPT more relevant? SPT, from my point of view, doesn't measure really a lot of things. Of course, if you have Sanzorite, you have to use SPT and make adjustments. So, you have to adjust your modulus of elasticity with different stresses, and that's why I like models that do that. I prefer some sort of a lab test or a CPT. It gives me a better idea for the continuity of the soil. On the SPT, I have to say this, right? It is a way that things have been done forever. I've seen like projects where there's 100 years of borings and 100 years of SPT with no lab test whatsoever. So you can't keep doing this with SPT forever. You have to get some quality samples out of the soil and test your soil properly. And of course, Christian, right, you can select the load step that is appropriate, a representative for getting your modulus of elasticity. That's why there is some engineering done required. I know what you're saying. Christian is making an excellent point here, that it's common practice of investors and owners that don't give importance to elaborate studies. Yeah, you don't have to go elaborate, I would say. It's not a challenge only in Romania. It's a challenge everywhere. But then, when you have to specify 20% or 30% or 40% more steel or concrete, they're not realizing the savings there. Okay, let me see. We got a lot of questions here. Who decides which method to put in practice beneficiary? Virgil, I didn't understand the question here. Which method to put in practice? You mean like which method to construct, which method is used? It depends. Sometimes who the owner is, And if it's a private job, really it's the designer or the building authority that has a certain way of accepting things. So that's how you make your decisions, and based on previous experience. Okay, so Christian says that you get only one for multi-layer, you get only one odometer result for 230 kPa, common practice. Yes, it is. I mean, I don't know if odometer moduli are really representative for excavations. Okay, I always there's a question from Alexander regarding monitoring for secant walls, structural integrity, deflection, etc. I always recommend putting an inclinometer, at least, optical targets, so you can correlate what's happening in case with your inclinometer. Make sure that if your wall is in soils and not in rock, that you extend the bottom of the inclinometer below the bottom of the wall, so you capture any wall movements below that. And if you have supports, you can put in some strain gauges, if you have struts and so on. And that, of course, depends on the budget that is available as well. So while it finds the top-bottom construction methods very fascinating, and there's a question, how easy is it to do that? Well, it's not easy. I think you can still build the floor slabs and everything else, so the load-bearing elements, and that's easy. The difficult part is really getting the small excavator to work under the floor slab and bringing all the material down under, on a small confined space. David, I think I've answered to that question. But the idea is that, for spring stiffness, there's various laws out there. One of them is based on using active and passive wedges and calculating the equivalent stiffness. Online as a video. There's a question from Christian, if I recommend 3D modeling in current element methods for deep excavations. It depends. If your model is behaving, I will still do a 2D analysis, but if it is a very narrow deep excavation, perhaps the only way to make it work reasonably is to do some sort of 3D modeling. And not necessarily, you can always back check, so you can come back and do a wedge analysis or a 3D wedge analysis and come back with a Ka factor equivalent and also run your 2D analysis that way. So the answer depends on your problem. I don't recommend 3D modeling for everything. I would say maybe 3D modeling is appropriate for 5% or 10% of the cases. I'll put it closer to 5%. For finite element analysis, at least. So thanks to everybody. If you have any questions, please contact me at my email, dimitris@deepexcavation.com, and I'll be happy to help you with all of your questions. Thank you.